We acknowledge the traditional owners and their custodianship of the lands on which we meet. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognize their valuable contributions to Australian and global society. So our speaker today is Joshua Silver, who is a research data officer at the University of Wollongong. He has 25 years experience with Unix system administration, network design, and macro support. He is currently assisting researchers at the University of Wollongong with managing their data storage and workflow needs. So I just hand over to Josh to start his presentation today. Thank you.
Okay, thanks, Sarah. Let's go. And just share screen. Okay, hopefully everyone can see that.
Yes, thanks.
Okay, great. So yeah, I suppose this is just to do about some of the work that I've been doing with the ACCS project, and in particular the 4.2 and 4.4 work packages. I've been with the cryoEM facility here at University of Wollongong for 3 years now. My background is a little bit of everything, predominantly desktop support, but a little bit of system admin and network design as well. And yeah, so I'm sort of here helping them with their data management and automation and just all things IT that go on behind the scenes of the research. So when I started here a few years ago, there wasn't really much automation at all. There was a little bit that had been put in place by the university's central IT. And it was kind of, actually, can you see my mouse pointer? I'm not sure. Anyway, it was section B on the diagram here. And it was something that was in place before I started. It did, you know, what it was designed to do, which was basically to stop the hard drives in the capture PC from filling up. But, you know, that was kind of its design goal. It worked, and it was pretty much, you know, what the central IT people had done. But we were starting to play with CryoSpark Live, and the, you know, design goals and what we wanted to achieve were a little bit different. We wanted to improve the, you know, the time it took to get those images across and be able to provide feedback to the researchers much quicker. So yeah, different goals. So yeah, so we basically reevaluated the automation. And had a look at what we could do to improve things. So the simplest step, the easy one, didn't cost anything, was just to look at what was already there and see if we could improve upon it. And you know, a little bit of digging around, and we worked out that that was actually going to be a relatively easy thing. It ran on a 10-minute timer, and it looked for files that were appearing on the image capture machine, and then anything that was over 10 minutes old, it moved across to the facility storage. I suppose a lot of those settings were very conservative, and I suppose once things they'd got it working, there was no real reason to go back in and change things. You know, it worked. And that was how things were for a couple of years. So, you know, we worked out we could easily drop a lot of those timings. There was no reason for it to run every 10 minutes. You know, we changed that to be every 3. And the files, you know, yeah, changed that to be files that were 3 minutes old as well. That was just to allow a little bit of time for the files to write to disk, because they were, you know, fairly large files. And also in CryoSpark Live, which is step C on that diagram, there was a how long it waited to import the files once they appeared on the file server, and we dropped that down to 1 minute as well. So these were all very easy. There was no, server upgrades, no network upgrades or anything like that. It was just a few little tweaks to what was already there, and made quite a large difference. We're able to drop the delay from when an image was captured to when it turned up in CryoSpark Live from 21 minutes down to just under 6.5. And that was basically, no real cost involved in doing any of that. We probably could have done even, better than that, but we were still, at this point, just playing it conservative and not wanting to, cause any sort of reliability issues. So that was all good for a little while, and things were going much faster. And there's that, I suppose, that saying of if things aren't broke, don't fix it. But also, we wanted to do some upgrades, get better quality, faster detector. So, we did. We had an upgrade in early 2022, upgraded the detector that was on our Cryos, and then moved the existing one across onto our Arctica. And the new detector came with a newer image capture machine compared to the old one. It was a faster computer, but the detector also puts out higher quality images much more frequently. So it was still kind of at the limits of what that PC could do, just running the image capture process. And we found that on this new machine, we were having some stability issues, and it seemed like it was our transfer task that was causing them. When it ran the CPU load, calculating which files to sort of ignore and which ones to transfer, seemed to cause some stability issues, which was a problem that we hadn't had on the older K2 detector setup. So we did a little bit of testing, and we worked out that yes, it did look like everything ran okay when we didn't have our transfer script running. The hard drives on that capture PC, they filled up in just under 24 hours, but it meant we could run it for a little while without the transfer running, do some tests. And that was great, but we still wanted to get those images off. There's no point, doing all of this if we can't actually get the images and do some processing on them, or if we have to wait until the image capture's finished. So when we were looking at things, when that transfer script ran, it used up about 20% of the CPU, just, I suppose, doing all the calculations of which files to ignore, which files to transfer. And that seemed to be what was causing the stability issues. So we manually just ran a test using another machine to run the transfer, rather than having the capture PC push the data to the file server. We used a machine in the middle to sort of, pull those images off. It was doing a lot of the, CPU load of working out what files to copy, and the capture PC just had to, do the file transfer side of things when it got asked for a file. And that dropped its CPU usage down quite considerably, down to about 2%. Obviously, the CPU on the DTN was doing the rest of it, but that wasn't a big issue because its CPU was mostly idle. I've already covered that bit. So we sort of switched things around to this kind of, what we called a pull rather than a push. So this was kind of the bit on the left was how things were, and then this is what we were testing. It did mean a few little changes in terms of, mapping network drives and things. The image capture PC, rather than mapping a drive from the file server, we had to set up a share on that PC, so that the DTN that was sitting in the middle could connect to both of them and then manage the transfer. But that all, worked fine, and our initial testing showed that it seemed to have solved at least the CPU load issue. So we sat down and did a bit of a rewrite of the existing script that had been set up a while ago by the central IT. That was all running on with PowerShell on Windows because that's what the image capture PC runs, but everything else in our facility was running on Linux. So it made sense for us to do a bit of a rewrite into Python and run it in Linux. I think, there is the option of installing PowerShell on Linux, but I knew Python a bit better, as do most of the researchers for different bits and pieces. So it was the obvious choice for us. One of the things we'd found when doing the initial optimization in their code, all the settings that we wanted to change were buried, hard coded in the code. So we wanted to pull some of those things out into a sort of separate config file just to make it easy to change settings. And we're also wanting to potentially reuse this to do the step D in that diagram, that the backups, which at that point in time was still a manual process, and being able to automate that would be very, beneficial. We also did a few little optimizations, again, just because, I knew Linux a little bit better. It's not to say that this couldn't have been done under Windows, but the systemd scheduler, we changed it so that rather than running on a fixed timer, there was just a pause between, when one job finished and it kicked off again. So we dropped that to just basically when one transfer finished, wait 30 seconds and then transfer the next one. And we didn't have to worry about, reducing the time and having one transfer run longer than whatever timer we had set, and then the second one kicking off while the first one was still going. We also changed the how long to like the files to ignore from 3 minutes down to only 2 minutes. And this last one I put a little asterisk after. When things were running on the Windows, the capture PC, when it was running, be it 10 minutes or 3 minutes, the transfer took about 60% of that time. So, if we sort of ran it every 10 minutes, it would take about 6 minutes to copy the files that were generated in that 10 minutes. With the DTN running everything, that dropped down to about 10 or 15% of the time. We hadn't really changed anything. It was still using all the same network links, the same machines. We had done a little bit of work with the DTN for other transfers down to the remote HPC and optimizing, network settings and things. But that was, I suppose, a nice little fringe benefit rather than something that we specifically changed. So what that meant is that, again, things went even faster. So we dropped that initial 21 minutes down to about 3.5 minutes now, which, given we were getting about 400 images an hour coming off the microscope, 21 minutes meant that you were 140 images behind. The 3.5 minutes meant that the researcher and what they were seeing on the screen was only 23 images behind, which, I'm not a researcher, but obviously the quicker you can see what's going on, the better. And then this is a separate bit of work that we did with the upgraded detector and getting the images, higher resolution and faster. Obviously, the data volumes coming off the microscope have gone up dramatically. And one of the things that happens now is that images that used to be an MRC format, kind of a raw image, now come off compressed as a TIFF image. And that helps mitigate some of that, increased data volume by compressing the file. And that's kind of the default now. But we had a whole bunch of existing data sets from the last couple of years that were still in MRC format and taking up a lot of storage space, both on, our facility storage server, and also, just in terms of, backups and things like that. And then, to pinch a line from Spider-Man and mangle it a little bit, with great data comes great storage requirements. So we were looking at what we could do to improve that. So there's a iMod suite of software that has a function for doing the file compression, kind of an after the fact thing. And we looked into that. The first stumbling block was that it takes a single MRC file as input and gives you a single TIFF file as output, which is great, but we had folders with tens of thousands of MRC files, and trying to do that one at a time was not going to be practical. So we wrote a little wrapper script for that, where we could give it a data set and it would search through and find all the MRC files. We also made it so that it could split them up into, whatever number of chunks we gave it, depending on the CPU in the machine, and run each chunk in parallel just to speed things up a little bit. And we could go through and compress some of our existing data sets, and save a bunch of space. So this is just a few of the data sets. We sort of went through the last couple of years, but these are just some of the ones I pulled out, just to show sort of what they were in terms of their size in terabytes as MRCs, and then what they compressed down to. We found we averaged about a 5 times compression, which was great. Some data sets would compress more, some a little bit less. But yeah, about 5 times was the average. And okay, we're at the end. So there's links to the 2 reports that I've done and to the GitHub repositories for where some of those bits of source code and stuff are. I think that's it for now. Happy to answer any questions, go back to any slides if people have questions, or elaborate further on anything that maybe I skipped over because I was a bit nervous and went a bit fast, and yeah.
Thank you very much, Josh. Can you please just copy and paste those links on the chat just in case that anyone wants to have a look? And
Sure.
I guess we're ready to open the floor for any questions and comments and discussion around that. So feel free to raise your hand or type any questions in the chat. Yes, Roland? Oh, Samitha?
Yeah, hi.
Yeah, okay.
Sorry, you go. No, someone else can go.
Yeah, go ahead. Sorry. Yeah.
Me or Roland?
So, okay, Samitha, we start with you.
Okay, right. Thanks. Thanks for the presentation, Josh. Great to see the compared to the benchmark and some of the improvements made. I'm much interested to know the technology behind it and the kind of tools that you have used to make those improvements. And
yeah, okay, sure. So the tool that we used for doing the transfer is one that's called rclone. It's a third-party transfer tool, a bit like rsync, or I suppose the reason we picked that one, we did look at a few options, just usual FTP and rsync and things like that. We liked it because it was something that could be run as parallel, in terms of multiple transfers running in parallel. And it also, because we were wanting to reuse it for our backup step, which is to a S3 storage, it had the it knew how to talk to S3 storage as well. And it was also one that that CloudStor recommended for doing transfers if you're using I mean it's multi-platform, but I think for a lot of our stuff, which is Linux, we could use it to send files up to CloudStor and stuff as well. So it was one, was a tool that we could use in multiple locations, and it was one that I'd already used in the past as well. So sticking.
What is it called again?
It's called rclone.
Okay.
It's just rclone.org. I can probably, I've got links to it in the transfer. Still, like, it's in the requirements. You need to download this, and I've got links to it. It's just arclone.org, I believe, is the website.
And in terms of the amount of volume of data that you are able to handle, I mean, in the order of terabytes, or how?
Oh, yeah, multiple, like tens of terabytes. So we use this for not just the I suppose the images coming off the capture machine, but we now have got this running for our backups as well across to the S3 storage. And that's hundreds of terabytes.
So for example, if you take 100 terabyte, how long will it take to transfer from one point to the other? You can define the points.
Yeah, so look, I suppose that's one of the, I mean, yeah, it does depend a lot on the two endpoints and the network in between them. Can easily see, 700 megasecond when I'm doing just an internal transfer between sort of our file server, and some of our different research groups have a NAS, like a Synology NAS, and we'll send their data set to them to go and process themselves. A few of them have their own CryoSpark on their own machines, and we'll get 700 megs a second across a 10 gig network link. Writes to backup are a little bit slow, and I think that's the S3 storage here at the university. It's designed for large amounts of storage, not necessarily performance. And we're actually, it's one of the issues we're running into at the moment, is that the microscopes are generating data so fast that we can't write it to backups at the rate that it's being generated. So that's something that we're looking into at the moment. Obviously, the microscopes aren't running 24/7. So once a data run has finished, that backup process catches up. But while it's running, that backlog of data that needs to go to backup, even when the script is running, it's being generated faster than we can write it to storage. So yeah, arclone, it doesn't have a few of the, I suppose, I know like rsync and FTP had some limitations with the encryption side of things being the bottleneck, because they were never designed for high throughput networks. I believe arclone is relatively new and has some of those sort of considerations taken into account. But yeah,
Okay.
we've not run into it being a bottleneck. And sorry, I just saw a chat message saying, and yes, we can definitely send out the slides.
Thanks, Josh.
Thank you. Levi? Yes. No more questions?
Just sorry, I'm just going back through.
Levi's on mute, I think, wasn't it?
I was on mute. No, I was going to say, so you're not using any other protocols like Aspera or Globus or any other thing to rapidly move the data between endpoints? You're just using the normal network?
Correct. We are using Globus for the transfer down to the remote HPC.
Okay.
But all of this stuff is internal. The capture PC isn't on the internet, so we can't run Globus on it. It needs to be able to talk to the Globus servers. So we are just using internal networks for getting the data to the facility file storage. Yes.
So is your rate determining step at the moment the bandwidth of your connections, or are you running into your drive speeds and things like that? And what's your slowest thing at the minute now?
So at the moment, yeah, look, it's that I suppose the capture PC has a 10 gig network and everything. Yeah, look, we're not running into any limits at the moment with the data generation coming off the microscopes. The network and the disk speed is definitely fast enough at the moment. I I suppose if we go back a few years, the storage server that we had back then, we were possibly limited by the disk speed, but that is something that the facility's upgraded recently, being a couple of years ago. Yeah, so that I suppose that at the moment the real limit is just how fast the detector on the microscope can generate the images. We haven't reached any other bottlenecks.
Okay, thanks.
Thank you. There is a question from Roland in chat.
Yeah.
So he's curious about how you handled cryoSpark and how far away is the data from the instruments and what was the delay time?
Okay, so so I suppose in terms of physical distance, yeah, the microscope is probably, I don't know, well, I mean, they're all in the one building, so we're talking, tens of meters, maybe 100 meters at most. I don't know where all the fiber and network cables run. I wasn't, I'm not sort of the network person, but yeah, definitely within the same building from those sort of steps B and C, which are the ones that we were concentrating on. So how do we handle cryoSpark live? Not quite sure what you're wanting me to explain there. We did have cryoSpark live running on some GPU machines, and they had the facility storage shares mapped, and they were just monitoring a folder and importing images with that 1 minute delay as they turned up on the facility storage server. So most of the the bit that we were working on was getting them off that image capture machine onto the storage server as fast as we could, I guess, without causing issues. Okay, so sorry, just reading the chat as well. So I suppose we had two steps, Roland. We had the first step, which was the live processing that was happening, in real time as the images were being captured, and then there was, data sent down to Massive at Monash for further, more detailed analysis or whatever. Yeah, sorry, I'm more IT than a researcher, so I don't have much of the details on, I mean, I've dealt with cryoSpark for quite a while and definitely spoken to people, but yeah, I haven't ever actually used it to run, analysis. I'm not capturing my own data sets, but yes, I know there was, yeah, the initial screening done in cryoSpark Live was done locally, and then the further processing in just cryoSpark or Relion was done down at Massive.
Hi, Josh. Can you hear me?
Yes, I can.
Hi, Josh. How are you, first of all? And that was really a good presentation.
Hi, Barney. Yeah.
Just asking you one thing. So you said that the transfer script was taking a lot of CPU memory, and you reduced that from like capturing the data from between the machine. So can you please explain more on this?
Yeah, well, okay, so we didn't really, reduce it any, we just moved it somewhere else, I guess. So when the script was running initially, central IT guys, they know Windows. That's kind of what most of their servers are. And obviously that was easiest for them, was to write a PowerShell script that ran on the capture PC. I'm not a Windows person. My background's Linux and Mac, and so for me, it was easier for me to run things on the Linux side rather than the Windows side. So what we found was when the script was running on the capture PC, it was using up a little bit of CPU. There's a few, it's working out which files to copy and which ones to exclude, and it's running a couple of parallel threads of to make the copy go faster and things like that. And we shifted that off the image capture PC onto a separate machine that was sitting there pretty much idle, at least the CPUs were, so we could shift that load off, have it run all the calculations of which files to copy and which ones not to copy, so that the capture PC, all it had to do was basically go, here's a file, here's a block of data, and didn't have to do any of the heavy CPU load that went with it.
Yep. Okay.
But
is there any role of CMTS in between, or like can you also directly capture the data from CMTS so that you don't have to transfer your data to CPU? And so as soon as the camera captures the micrograph, that goes to the CMTS unit in the microscopes, right? And then they are being pulled to the CPU, right? So is there any possibility to directly capture from the CMTS so that you don't have to like worry about the CPU?
Yeah, look, that would be an ideal solution, and it's definitely one that we'd love to test. Unfortunately, the vendor doesn't support that. They only support writing to the capture PC. If we could just directly mount our facility storage server and then have it saved directly there, that'd be great. It would also, I suppose, be an issue if there was ever a network issue, or we needed to reboot the server, where at the moment it's writing to that local capture machine that's attached to the detector. And if we have to, restart something, or the network drops out for a short while, less than the 22 hours or whatever it takes for those hard drives to fill up. That process will keep running. We can get the network fixed. We can reboot our machine, do whatever we need to, and then that script will kick off and resume doing the transfer. So
makes sense.
Yeah, that would save a little bit of time, and it would be lovely to do, but that's not not something that we can do at the moment, or at least it's not supported at the moment.
Yep. Great. Thanks for your time.
Josh, there is a question in chat. Can you please elaborate on push and pull technique that increased the transfer speed?
Yeah, so that one, I did put a little asterisk after that one. So, I mean, I suppose just in terms of the push and pull bit, that was more about the capture PC pushing the data to the facility storage server versus the DTN that was sitting in the middle pulling the data off the capture PC, and that was to do with the dropping the CPU load. Why things went all of a sudden way quicker, given that we were using the same machines, the same drives, the same server, the same network links and all that sort of stuff. No huge, we made this change and it went way faster, and can't really point at any one thing. I suppose we did change a lot of things, and that's the often why you'll sort of change one thing at a time and test, and then change one thing and test, is that we changed a few things, and it could be that things are more efficient on Linux versus Windows, which I'd like to think so, but I'm a bit biased. The DTN that we were using in the middle, we had done a lot of work with at this end with Monash, with RNet, to optimize the transfers, sending data down, and tweaking some of the network stack settings and all that sort of stuff. So potentially that machine was better at transferring data than the capture PC. So I can't really point you at any one thing that say, hey, do this, and the transfer speeds are going to go through the roof. We actually ended up slowing things down because we were worried that potentially we were now going to create, we'd fix the CPU load issue on the capture PC, but we didn't want to introduce an IO issue if we were sucking all the files off the capture PC just as fast as we could, and then that might impact the detector writing images to the disk. So I suppose the push version, the original version, it ran 4 parallel transfers. We're running 2 now, just to try and I mean, we haven't had any issues, and that's one thing that we could probably, put back up if we ever ran into the fact that we weren't copying the files off the capture PC fast enough. But yeah, we dropped that down to just 2 parallel transfers, just to try and avoid, creating a whole new problem of disk IO kind of, issues. Hopefully that goes some way to explain, answering your question.
All right. Thank you, everyone. Is there any other questions? Yes. Yes, Kieran.
Hi, I just wanted, so when you're doing the MRC to TIFF conversion,
Yes.
was that a slightly lossy process? I know you saved 5 times the amount of data, but was it slightly lossy during that time?
No, that was all lossless. Sorry,
That was all losses. Okay,
Yeah,
I just wanted to clarify because, yeah, cool, thanks.
So that was definitely lossless. We did a bunch of tests first, making sure that running things through CryoSpark and Rely On and stuff, just to make sure that there wasn't something going on with the data and its usefulness. If we were compressing it and all of a sudden it became junk data, then
we have bad quality images. We have a predilection for imaging molecules which image really badly, so any lossiness out there could be a problem. But if you've tested it all, that's good.
Yeah, and the new K3 detector, they come off as TIFFs to start with. We don't get them as MRCs anymore. So that that was kind of why we went back and had a look at, well, hey, we've got all this old existing data.
Yep.
And yeah, if we can slash the amount of storage space we need for backups and just on the facility storage, or at least we can now fit more stuff in the same space, so to speak, then that's great as well.
Cool. I might look into that as well. Thanks.
Yep.
Thank you. I can't see any other questions in chat, but if there is any comments or question from the audience, we can discuss. Otherwise, we will wrap up the session. All right, I don't think that there is any other question. Lots of thanks coming in chat for you, Josh. Thank you very much for a great presentation, and thank you everyone for joining us today. We will upload the recording and the slides and imaging tools, and I will share the links when they are available with you. Thank you very much. Have a great day, everyone. Bye.
Thank you.